All right, simple concept that can oftentimes be blown way out of proportion is the conservation of energy. Okay. Now, I've written a couple of very general statements. Okay, and obviously it gets more complicated than this, but if you keep this idea in mind, I think it helps. Okay, where if I say the energy initial must equal the energy final, or energy at the beginning, original, must equal the energy final. All it means is this: if you start any activity with a certain amount of energy, you have to be able to account for all of the energy before and after that activity. Okay, and it says that the total energy in a system is constant, meaning if I have 100 joules to start, I better have 100 joules in the end. However, that energy can change forms. Okay, so how am I going to use this to solve problems? Okay, so if I've got this example problem, a ball falling from 2 meters to the ground. Okay, if at the very beginning, this is the ball, if it had a velocity of 0 at a height of 2 meters, we'd have to look at it and say, okay, what type of energy do we have? Okay, so energy initial and energy final. Well, the energy initial would all be gravitational. They would all have U. Okay, or UG. But when it's at, say, this particular height, when it's fallen to this particular height, it now has UG, but it also would be moving at this point. It would have some velocity. It's falling down. So it would also have some kinetic energy. So I'm going to label this UG1 and UG2. Okay. Now I can use this information to help me solve for things. Like, for example, if I want to solve for the velocity at this point. All right, well, the initial gravitational potential is mgh. This one, and let's call this height 1, and this one is mgh2, and the kinetic energy is 1/2 mv squared. Okay. Now you'll notice that we've got mass in everything, so we can get rid of that. Okay, and now we've got two different heights and that are known, gravity, which is known, and then we have the ability to solve for a velocity. Okay, so this idea that started off as, okay, my initial energy must equal my final energy, that's true. The total amount will be the same. They're still equal to each other. So whatever I had here must be accountable over here. However, we've noticed that the types of energies have changed. They've diversified in this case. Okay. Now this would be at h equals 1 meter. Okay, and I'm not going to solve the problem. You can go ahead and solve it if you'd like. But let's also apply this to, say, solving for the velocity just before it hits the ground. So let's say this is at height equals 0. Well, again, if I say the energy initial equals the energy final, again, it starts off as potential. And down at the bottom, if you look at this, okay, I've listed that the height is 0. Now, this is oftentimes a problem for people because we know that when it hits the ground and it's actually on the ground, the velocity will be 0. That's not really that important for us. We want to know how fast is it going when it strikes the ground. Now, we used to do this type of problem with kinematics all the time. What is the velocity just before it strikes the ground? We can do the exact same thing with energy transfer. So if I said just before it hits the ground, it would be at a height that is so small that we could basically call it 0. Well, then all of this gravitational potential energy would have been converted into kinetic energy. And again, I would have mgh and 1/2 mv squared. The masses go away, and I would be able to solve for the velocity as long as I knew the height and the value of gravity, which are known. Okay, so this is an example of how you can use conservation of energy to help solve something. So let's do another problem. And now again, I'm just going to set these up. I'm not actually going to solve them numerically. But here's another one that we could do. Find the velocity of a dart being shot from a dart gun. Okay, now one thing to understand is that inside of a dart gun, and I know everybody's impressed at my drawing, okay, there's a spring, okay, and you can compress the spring, Okay, and when you reach a certain point and the trigger clicks, it releases the spring and it pushes the dart out of the gun. Okay, so here's the deal. If I was given, say, a value for the spring constant in the gun, okay, and I was given how far the spring compresses, so it compresses 10 centimeters, it's a pretty big spring, okay, and you're given the mass of the dart, we ought to be able to come up with a way to solve for this. Now, if again I look at the energy initial versus the energy final, the initial type of energy that it has would be elastic potential. All of it would be stored as elastic potential when you're squeezing the gun, when you're compressing the spring. And what happens is after the spring releases and uncoils, it's going to transfer all of that into kinetic energy. So again, I would have 1/2 kx squared equal to 1/2 mv squared. So again, these halves can go away. They're in both terms. Okay, but as long as I knew the k value, which was given, and the x value, which was given, and the mass, which, be careful here because I wrote this in grams, so that's got to be 0.005 kilograms. Yes, all your masses must be in kilograms. Okay, then we would be able to solve for the velocity of that dart. Okay, now so far these couple examples have been easier examples. Okay, how about I give one like this? Oftentimes we talk about things where energy has been dissipated. Okay, so dissipative forces are things like friction. Friction causes us to, say, lose, and I'm using lose, and as I'm saying it, I'm putting quotation marks up because you're not really losing it. It's just not, and it's no longer present in, say, that current system. Maybe you lose it as heat, something like that. But let's say I had a question that said, find the value of friction, and the friction force, I guess I should say, if the cart covers 400 meters of track. Okay, now, if you look at this picture, I've got, say, an object that's at a height of 400 meters and a velocity of 0. So let's just pretend it's teetering just on the edge, okay? And then it goes down the track, all the way down the track, but it only reaches a height of 25 meters on the other side, and it's now got a velocity of 0. Well, it had to have lost some energy there, because if I really look at this situation, energy initial is energy final. In the beginning, it would have some potential, some gravitational potential. Okay? And in the end, it would also have gravitational potential. But those are different values. So again, I'll say G1, G2. So what exactly happened along the way? Well, if there was friction, it would have used some of that energy. So I like to think of it like this. If I don't have the same amount of energy, then I had to lose energy. Some of the energy must have been transferred into a different form. Well, if it was transferred into a different form, then work was being done on the system. Okay? Which means we have to account for that. And in this particular case, that amount of work is done by friction. Okay? Now, you need to be a little bit careful about this, because remember that work is a force parallel to a displacement. This is the most basic form. Okay? Now, keep in mind that as we're going down this, understand that the displacement, no matter what, at any point in time on the cart and the force are always parallel to each other. At anywhere on here, the force of friction would be acting against the direction that you're moving, but they would still be parallel. Okay, so you might end up seeing F is delta x cosine of theta for the force that's always parallel to it, but keep in mind if it's opposite direction, then this is 180, which makes the work negative. So if I was going to have negative work on here, I'm going to put it on this side. I'm going to add the work, but that work is technically a negative amount of work. Okay, so what I would end up with here is an mgh plus, okay, well, that amount of work done, okay, would be my friction force, which is negative in this case, times the displacement, which is parallel to that. That would equal my new mgh on the other side. Okay, and this is a way where, again, as long as we knew the mass, and I didn't give you a mass, but you maybe need one, and you had gravity and a height and a displacement, which I gave you that right there, okay, and a new height, 25, you ought to be able to actually solve for forces in these types of problems. Okay, we'll have plenty of opportunities to go through more of these types of examples, and I know the picking which side the work needs to go into can be a bit tricky, but hopefully that starts you off on the right track. All right.